Okay, so in the previous video we have seen what is meant by two elements in a Euclidean ring being relatively prime. So in our attempt to prove similar results that we have already come across in the ring of integers, we next state this one, the fifth lemma. Let R be a Euclidean ring. Suppose that for three elements A, B and C in R, A divides BC, but A and B are relatively prime. Then we have to prove that A divides C. Okay, looking at this result, it reminds you clearly of a similar one that we have in the ring of integers, and the proof is also similar to what we have already seen there. We start off with this part of the information given to us. Since A and B are relatively prime, the first lemma, if you recall, it says that the greatest common divisor of two elements has a particular form in terms of the elements. So from that lemma, lemma 371 implies that the GCD, which now is 1, can be written as lambda A plus mu B. For some elements lambda and mu belonging to the ring. So now next what we do, we multiply both sides of this equation by C, by the element C. This implies C is equal to lambda AC plus mu BC. Now since A divides lambda AC, A divides lambda AC, there is it's almost obvious because this element has A as a factor, and also A divides mu BC. That is because it's given that A divides BC, so we know from properties of divisibility that A also divides any multiple of BC. So since A divides these two things, A will divide their sum, again from one of the properties of divisibility. So from then we have A divides lambda AC plus mu BC, which is nothing but C. C is equal to lambda AC plus mu BC, and that's what we wanted to show, that A divides C. So this completes the proof. It's a very simple one, but a very useful one. We will see it being used in connection with divisibility by prime elements. So now we turn to prime elements in a Euclidean ring. Our aim is to show that they mimic just the ordinary prime numbers. So we start like that. We want to show that prime elements in a Euclidean ring behave just like the ordinary prime numbers in the ring of integers. So let pi and a be two elements in R, where R is a Euclidean ring and pi is a prime element. Okay, now from these two things, what can we conclude? Let us see. Let us first consider the, I should not say the, but I am still saying GCD of pi and a. Note that from our previous results from GCD, actually from this one itself, lemma 371, it says that in a Euclidean ring, two elements have a GCD if at least one of them is non-zero. Now we don't know about a. A may very well be 0 because a is any given element in the Euclidean ring R. But pi is given to be a prime element. So from the definition of prime elements itself, pi is a non-zero element. Hence, by lemma 371, this greatest common divisor exists. And from definition of GCD itself, we have this also. GCD of pi and a divides pi. It also divides a, but we will use that divisibility later. So right now we start with this one. Since this divides pi, pi must be a multiple of the GCD. U for some element u belonging to R. Now note that we have expressed the prime element as a product of two elements in R. So from the definition of prime elements, one of them has to be a unit. Since pi is a prime element, either pi comma a is a unit or u is a unit. If pi comma a is a unit, then by definition of relative primality or relative primeness, whatever you want to call it, pi and a are relatively prime. Then they are relatively prime, and we have already seen this. We may as well take their GCD to be the unit element 1. This happens when the first factor is a unit. Now assume u is a unit. What happens if the second factor is a unit? U is a unit. Note that GCD of pi and a also divides a. Okay, from the definition of GCD. So A is equal to pi comma a times v for some element v in R. Okay, now it is given that U is a unit, right? Then from this equation, what do we get? Oh, sorry, this is V. Note that since U is a unit, we can take U on this side, making it U inverse. Speaking loosely, or if you want me to say it more formally, you multiply both sides by U inverse. You will end up with pi U inverse equal to pi comma A. So we can replace pi comma A with pi U inverse. Pi U inverse V. So now you see that A appears as a multiple of pi, that means pi divides A. Which implies pi divides A. Thus we have either this or this. This is true for any prime element pi and any element A in a Euclidean ring. Either they are relatively prime or the prime element divides the other element. Now using this, we can easily prove the next result, which is the sixth lemma. So it states that there is a, this is the one that we were talking about. If pi is a prime element, in a Euclidean ring R, and pi divides AB, where A and B are any two elements in R, then pi divides A or pi divides B. This is just like the result which says that if a ordinary prime integer divides a product of two integers, then it divides at least one of them. So it's just the version of that result in our general setup of Euclidean rings. So we see the proof. If pi already divides A, then there is nothing to prove, or we are done. We can write that also. So assume that pi does not divide A. Okay. So from our previous discussion, we have seen that one of these two things has to be true. So if pi does not divide A, clearly this is not true, because here we have the negation of this. So that means this must be true. Then from the discussion above, pi and a must be relatively prime. Now pi divides ab and pi and a are relatively prime. So from the previous lemma we have that pi divides b. Thus from lemma 375 and this ends the proof, that is pi either divides a or b. And this result clearly has a general version which involves a product of not just two elements but any finite number of elements, and that appears as a corollary if pi is a prime element in a Euclidean ring R, and pi divides a1, a2, etc. an, where they are coming from the ring, these elements. Then pi divides ai for at least one I, where I varies between 1 and n. And this corollary can easily be proved using this one and induction. This one will help us create a basis for our induction, and then it's quite straightforward. So I am not even mentioning that the proof is very easy and it can be done with induction. So you heard me say, and that's it. Now next we look at the other half of the unique factorization theorem. Note that we have already shown in the previous video, I think, that any non-zero non-unit element in a Euclidean ring has a factorization as a product of finitely many prime elements. Now that is one half of the unique factorization theorem. The other half involves the uniqueness of that expression of that element as a product of prime elements. Although uniqueness is not exact uniqueness just like what we have in the ring of integers, but here also in a sense the expression, the factorization is unique up to associates. Let us state the theorem. So this is theorem 372. This is as far as we can go in our attempt at generalizing everything in the ring of integers to the setup of Euclidean rings. So this one has the name also, unique factorization theorem. And the statement is this: let R be a Euclidean ring and a not equal to 0, a non-unit in R. That is, we have taken a Euclidean ring and we are considering a non-zero non-unit in R. Then we already know it has a factorization. What happens if it has two factorizations? Suppose that let me write from here. A is equal to, this is one factorization, pi 1, pi 2, etc. up to pi n, and at the same time it has another factorization as a product of some yet maybe possibly different prime elements. Also the number of factors may differ. May differ means as of now, at the time of stating this lemma, we don't know whether n and m are equal or not. We will prove that they are equal, but that has to be proved. Where the pi i's and pi j prime are prime elements in R. Okay, so this is the situation. Then n has to be equal to m. The number of prime factors will be equal, it's constant, and each pi I he mentions the range of variation of I varies from 1 to n, is an associate of some pi j prime, and conversely each pi k prime is an associate of some pi q, say. You have to understand that these are all variables, okay, k, q, etc., I, j. So this is the unique factorization theorem, the second part of it. Note that how it is different from the one that we have in the ring of integers. In the ring of integers we have absolute uniqueness, where say we are writing 6 as a product of 2 primes, then we have 2 times 3. But if one one does not restrict the primes to be only positive primes, then we actually have another factorization of 6 as minus 2 times minus 3. Okay. The difference between these two factorizations is only in the fact that 2 and minus 2 are actually not equal. 3 and minus 3 are not equal. But you can see that this clearly shows what is happening in the general case. Although 2 and minus 2, they seem to be different primes, they are different primes, but the factorization is unique in the sense that the number of factors is 2 in both the factorizations, and 2 is an associate of minus 2, 3 is an associate of minus 3. Each element in each prime in one factorization is an associate of some prime in the other factorization, and conversely. Why that is so? Because 2 can be written as minus 1 times what I am saying is this: minus 2 can be written as minus 1 times 2, and minus 1 is a unit in the ring of integers. So I have already said that using units, if we have one GCD, we can create more GCDs. Like that, using units, if we have one prime number, we can create more prime element, then we can create more prime elements. So the only difference between different primes which look like they are related is that they are associates. As far as properties of Euclidean rings go, two elements that are associates seem to behave exactly similarly. Anyway, so let us now look at the proof. So in the ring of integers, we gain absolute uniqueness by restricting ourselves in the positive part of that ring. So the proof goes like this. First we have to prove that n is equal to m. So we suppose that that is not the case, and we try to arrive at a contradiction. Suppose n is less than m. Okay. Since pi 1 divides this product clearly, because pi 1 is a factor in this product, so pi 1 also has to divide the other product. Pi 1 prime. Okay, let me not write pi 2 prime because I won't have space. It means the same thing, this one and this one. We have this. Now look at this. Pi 1 is a prime element which is dividing a product of some elements. So from this corollary, we know that pi 1 has to divide one of the primes here. Then by the previous corollary, pi 1 divides pi I, say pi I prime, for some I lying between 1 and m, because I varies from 1 to m. Then pi I prime is equal to pi 1 times u1 for some element u1 in R. Okay. Now pi I prime itself is a prime element, and it has been written in this form as a product of two elements. So from the definition of prime elements, one of these two factors has to be a unit. Note that that unit cannot be pi 1, because pi 1 is itself a prime and by definition non-unit. So the only possibility is that u1 has to be a unit. So since pi I prime is a prime element and pi 1 is not a unit, u1 must be a unit. Okay, now incorporating this relation here, what do we get? Or not here, but in this equation. Now the equation phi n is equal to phi 1 prime, phi 2 prime, phi m prime implies is equal to phi 1 prime, phi 2 prime, phi I minus 1 prime. Then we will write pi I prime. In its place we can write pi 1 u1. I plus 1 prime etc. up to pi m prime. Or now, since every Euclidean ring is an integral domain and prime elements are non-zero, so we can cancel pi 1 out from both sides. Doing that, we will get pi 2 dot 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 up to pi n is equal to pi 1 prime, pi 2 prime, pi I minus 1 prime u1, pi I plus 1 prime, pi n prime. So 1 prime has vanished, pi 1 from both sides, and that has left us with a unit element. We can now repeat the process with pi 2. Note that every time we take 1 prime, we consider 1 prime and run this argument, it will vanish. At the end of the argument, it will vanish. We repeat it with pi 2, that will also vanish. Then we repeat it with pi 3, that will also vanish, until we do it with pi n, and then we do it with pi n, that will also vanish. What is what is guaranteeing us that for every pi I on this side, we will have a pi j prime on that side, which we can use in this argument, and that guarantee comes from this: n is less than m. So for the primes that we have on this side, we will always have a sufficient supply of primes on the other side, because m is greater. We will never run out, till we get to pi n, and then we also run the argument with pi n. In this process, we will never run out of primes on this side. Okay. So repeating the argument with pi 2, pi 3, etc., pi n, we will ultimately end up with an equation of the form of this form. One, or let me just write like this: 1 is equal to u1 u2 un times what can I write here, s So every time we are taking one prime vanishes, it leaves a unit also. So n primes vanish from the left hand side, they leave us with n units, where we have to state what these symbols mean, where u2, u3, etc., un belonging to R are units, and S is a product of how many primes on this side? The excess of m over n, because m is greater than n. After cancelling out n factors from this side, we will be left with m minus n factors. Product of m minus n or m minus n prime elements from among these primes. The reason we are writing this as S is because we don't know which primes from the right hand side are going to get cancelled.